Morning, everybody. Welcome to Fraunhofer. Welcome to the Plasma User Meeting from Hiden Analytical for 2023. It's great to see so many people here. So all thank you for coming. Your attendance is very much appreciated. Before I get started, a couple of notes on the agenda. So you've got a copy of the agenda on your desks. We have some transport problems from the guys from IOM Leipzig. So Dr. Bundesmann's presentation will be now after lunch, and we can cross our fingers that he attends by lunchtime. So the other presenters are going to shift upwards by one. So after Sam, we have Amir Abbas, and then we have Dr. Kalfus after Amir. So yeah, good news wise, lunch is at 12 at midday, and please don't pay for your lunch. That's on us from Hiden. Okay, so please enjoy your lunch and refreshments. So I'm Dr. Dane Walker. I'm the marketing manager from Hiden Analytical, and my colleague here is Sam Bort, as well as Andre Kaiser, and I'm sure you've met Andre before, and most of you have met Sam before as well. So I'm going to do a little introduction to Hiden Analytical. As I'm sure a lot of you have come into contact with us before, I'll give you an insight into what other applications other than plasma that we address, as well as a bit about what we do. So Hiden has been in business for more than 40 years. So last year we had our 40-year anniversary. And since that time, we've been privately owned. We're based in Warrington in the UK. We have the factory there in the sunshine with around 100 staff. We're privately owned. We've been in business, like I say, in the UK for around 40 years. We've got a US subsidiary based in Michigan, which addresses the whole of the US. And we have, since 2019, we have Hiden Europe based in Dusseldorf, which Andre Kaiser is the sales manager for. And we provide a local presence all around the world. So we have offices all around the world with many staff and agents all around the world. One thing that we do pride ourselves on is our customer support. So we have lifetime email, telephone support with all of our systems. So we're still providing support for systems that are up in excess of 30 years old. So our main business is mass spectrometers. That's probably 99% of what we manufacture. So our ranges can contain gas analysis, dissolved species analyzers, catalysts, catalysis and thermal analysis instruments. We have systems for thin films and surface engineering, as well as plasma, surface analysis, and RGA systems as well, all based around quadrupole mass spectrometers. So for gas analysis, we're looking at measurement of reactions from gas streams. So our new system here, we can see the QGA 2.0, and that was released 2 months ago here in Germany. And that's our next generation gas analyzer. That's a real-time capillary sampling gas analyzer. We have dissolved species analyzers for looking at dissolved species in liquids, and for electrochemistry, so we can look at real-time electrochemical reactions as well. And we also have up to the huge HBR60 system, which has an integral EQP plasma analyzer, which is a system for analysis of neutrals, radicals, and ions, which you may have come into contact with. So we have a wide range of applications for gas analysis, as you can see there, and we're really driven by the applications that we address. So for electrochemistry and battery development, we have DEM systems, so differential electrochemical mass spectrometers, which look at the dissolved species in real-time electrochemical cells for battery development and things like that. We can also look at environmental applications where we measure radical VOCs in seawater. For mud logging as well, we have systems for oil and gas. We look at catalysts, we look at fuel cell reactions as well, all the way to real-time human breath analysis, where we're looking at low-level VOCs in breath analysis as well. For surface analysis, we have the TPD workstation, which is temperature controlled desorption, temperature programmed desorption, where we're looking at samples such as dissolved hydrogen in steels or deuterium in steels. So we heat up the sample and then measure the species coming off with our quadrupole mass spectrometers. We have SIMS, so we have secondary ion mass spectrometry systems with integral ion beams to locally analyze surfaces. We work with ion beam etching systems, so we have ion milling probes as well. And we can look at, we have custom softwares for elemental imaging and surface mapping. For plasma diagnostics, as you know, we have the EQP, and we also have the HBR60, which is the molecular beam mass spectrometer system, which is the atmospheric sampling or round atmospheric sampling plasma system. And we can analyze neutrals and radical species using our plasma sampling mass spectrometers. We have more simple vacuum diagnostics with residual gas analyzers. So these are bolted into process chambers. We can look at low levels of contaminants. We can look at quality of the species inside the process chamber. We can do real-time monitoring. We also have more high-performance systems for fusion systems such as the DLS-20, which is a 20 mil quadrupole, which can separate, for example, helium and deuterium. So again, there's some more application areas of industry that we address. So we have biotechnology, oil and gas, semiconductor, aerospace, nuclear, solar industry for the SIMS, and obviously plasma coatings. In research, we have very similar again. We address a lot of different research avenues. So we have electrochemistry is a huge one at the moment. We have materials analysis, space research, nuclear fusion, and biotechnology. So what our key to our success as a company and how we like to work is that we address the application, we work with the end user, and we have application specialists that are specialists in their avenues of research. So we do try and understand the application as well as we can to provide the correct solution for the end user. So we are quite flexible in that we have a full design team, we have a full software team, so we can customize our products to address the end user's requirements, and we do that quite a lot. Some recent customers of ours, so we again worldwide customers for semiconductors, aerospace, and government research labs. And universities as well. So we're proud to work with all these customers, and we see that we're working very closely with them. So this is us this is our HQ in the UK with our contact details, and then I'll say a little bit about the team with Hiden Analytical Europe. So we have Andre Kaiser here, we have Sashin and Jürgen, and also Wolfgang, and now my colleague Luke Wells. So that's our team based in Germany. So between them, they address the whole of Germany and Austria. So I'd like to pass over to Sam, and if there's any questions, please raise your hand while Sam gets sorted.
Thank you.
So Sam is one of our application specialists for plasma, and a lot of you will know Sam from installations and trainings.
Okay, thanks, Dane. Hello, everyone. So yeah, as the title says, I'd just like to talk briefly about some recent advancements that we've been making to the product line. I know some of you are probably already aware, but I just want to make sure everybody is up to speed. So yeah, so the three things I want to talk about is multi-channel scalar mode, the EQP20, and dual zone operation. So before we start, I thought I'd show you one of our test chambers back at the factory. So a lot of the data that I'm going to show you today was done using this. It's also used for testing all the new instruments that we ship out. And if you return any for maintenance, this is how it'll be tested before we ship it back to you. So it's a capacitively coupled plasma. The view through the window, you can see in the top corner. So the electrodes on the left, the EQP is on the right. Typically keep it about 5 to 10 centimeters away. So 13.56 megahertz plasma, so we have the matching network, and we can also pulse the plasma using the function generator, so we can do time resolved studies as well. So the time resolved measurements, this is where you have a repeating event happening, usually multiple times per second. And what people want to measure is the time evolution of the different plasma properties. So I just got an example from the literature there showing the 3 different plasma species and how they evolve over the course of a pulse. So the standard gating that all instruments are supplied with, it's a boxcar averaging technique. So we supply the instrument with a synchronization signal at the plasma frequency, and then we choose a window of time within the pulse where we can acquire the data. And we can change the position and the width of the pulse with the 2 parameters. It works really well, but it does have a weakness in that the narrower you make the acquisition window, the lower the effective duty cycle of the measurement is. So the instrument ends up scanning for a much shorter time, and it's just waiting for much longer. So to get around this, we developed multi-channel scalar mode. So it's works in the same way with the synchronization signal, but instead of just a single acquisition window, we now have many, up to around 6,000. We call them bins because we're emulating a multi-channel scalar card. So the main advantage of this is just the speed. The instrument's acquiring data for much larger proportion of the time. We'll do that. So what this looks like is this is a comparison between the two. So this was done on that chamber. 1.7 kilohertz pulse frequency, 150 microseconds pulse duration. You can see the data's roughly the same, but it's the acquisition time. So 8 minutes versus 9 seconds. And that's at quite a high pulse frequency. If that was, say, 170 hertz, more like a high PIMS or something, then 80 minutes versus 90 seconds. Suddenly a lot more things become possible. So this is looking at a single energy, but it's also possible to do the same scan, but for multiple energies, and then plot them in 3 dimensions. So if we do that, that's what we get here. So we've got ion energy down here and time going up there. And if we take slices in this direction because it acquires the data this way. If we take the slices horizontally through here, we've acquired all of the ion energy distributions at the different points in time. So I think this one was a 1 microsecond resolution, and then after you've acquired the data, you can then extract the ion energies after the fact. So I just chose some where they look a little bit different for that. So the advantage is you can just get all the data, shut down the process, and then get the ion energies afterwards. Okay. So the next thing I want to talk about is the EQP20. So it's called the EQP20 because it's got 20 millimeter quadrupole rods. So the 3 EQP members of the family are shown. So we've got the EQP6, the EQP9, and now the EQP20. So the advantage of going larger with the quadrupole is it improves the transmission through it. So that gives us higher sensitivity. So in the table, the important one is the ratio. So at the low masses, it could be up to 16 times as sensitive as the 9 millimeter. And that advantage does drop off at higher masses, but still up to 5 times the sensitivity. Because it's larger and it's harder to drive, the mass range is slightly limited compared to the other one, so it's only a maximum of 1,000. Here's a picture of one. So it's the same mounting arrangement, all the same, everything down here is the same, so we can still do magnetic shielding, water cooling, driven electrodes, they're all the same. The only difference is the quadrupole section here, which is much larger. So sort of linked in with the EQP20 is the dual zone operation. So all of our other quadrupoles run in what we call zone 1. So this is a stability diagram. So normally it would be when you're sweeping the mass, you're increasing the RF and DC volts, and hopefully just skimming the top of these stability regions to do that. But there is another stability region, which we call zone H, which is at much higher RF and DC volts. So the advantage of operating here is just greater resolving power. But due to the very high voltage, that does limit the mass range. So it's only available to 0 to 20 AMU. So for that reason, we make it user switchable in software. So you can still do zone 1, 0 to 200, but then you get this high resolution mode of 0 to 20. We originally developed it for fusion research, looking at sort of around mass 4 for helium and deuterium. And that's some example data that I got from the sales stuff here. So the red line is zone 1, where there is some separation, but it's not fantastic. But then green, as soon as we switch to zone H, it's much improved. And then it mostly replicates the same on the right-hand side, but this one here, which is the helium-3 isotope with HD+, that shows the maximum resolving power we can get, which is 0.005. So as you go up in mass, it's not possible to do 0.005, but we can do this. So this was again done on that chamber, just using the residual water in the chamber and the argon in the argon plasma. So there we can separate 0.028 AMU. So these will both be a nominal mass of sort of 18. So then because it's an EQP, you can also do the ion energy distributions on those if you're expecting them to be different. I chose to do the MCS on it. So there is a difference there. So the two ions do behave differently when it's a pulsed plasma. And without that resolving power, you wouldn't be able to separate those. It would be an average sort of the two. So yeah, I think that covers it. I don't want to take much more every time. So I can answer any questions now, or if you want to come and find me over lunch or whenever. Yeah, sure.
One question I have right now.
Yep.
Thanks for your presentation.
Okay.
My question is for the time resolution measurement, then the distance from the EQP to the plasma source matters a lot. How near you have to go to the plasma source to get decent time resolutions in the nanometer range, as your nanosecond range you showed right now.
Yeah, so it's not something I've tried, but yeah, as you move further away, you would expect them to perhaps smear out slightly. Yeah. Yeah.
What are the options to adjust the system to vary the distance of the EQP to the
we could, if that was so we have a standard test routine. So we try and position the EQP when we're testing it to send out to a customer in the same position so that we can use various measurements that we take as benchmarks to make sure it's performing properly. So that's the main function of that chamber. But if, say, we had a special request to do that as part of the testing process, then yeah, we could fit a Z translator to it and position it differently.
We are still, in our case, are limited. We have our chambers, they have large size, and then we have some 1 meter difference between the measuring device and the plasma source, and this is a lot. So you have flight time effects, and this is your time resolution.
Sure, yeah. So that's where you would.
Temperature problems, temperature-related problems.
Yeah.
It was also a question. Did you cover some temperature problems during this measurement when you made the time resolution?
No. So it's running at quite a low power. This would be sort of 20 watts, 20 to 60 watts, depending on what we're doing. And then when we're pulsing it, the duty cycle is quite low. So. Anybody else? Yeah.
Thank you for the presentation.
Thank you. It's okay.
Maybe I didn't understand it correctly, but did you say there are 2 zones which are dependent on the different mass ratios?
Yes. So it's a sort of a stability region. So so it's at a certain ratio of RF to DC volts and magnitude that will allow ions of a certain mass to pass through. So this is for both of the yellow and the red are both for mass 20, I believe. Yeah. So you'll get transmission both in the red zone and the yellow for that. It's just the magnitude of the RF and the DC that matters.
So it's not like the mass spectra is dependent on the mass numbers, and sensitivity is different to different mass numbers? Because if that is the case, then it would be hard to compare the relative quantity of the gases.
Yes, to compare between, if you wanted to do some measurements in zone H and some in zone 1, you would have to calibrate between the two. So perhaps do an RGA measurement with the internal ionization source, or perhaps with the plasma just in a steady state, make one measurement with zone 1 and then one with zone H, and then you can work out the sort of the correction ratio in the two.
But if you measure in zone 1, although there is no difference in the sensitivity to different mass numbers, right? If we measure smaller mass numbers or higher mass numbers?
Yeah, so you get the mass-dependent transmission. So the transmission does fall off at the higher masses. So that's a well-known thing. You can usually get I think we publish a rough table of that, and there's a relationship there for that.
Yeah. The system already takes into account this difference in the sensitivity.
Well, that would be something you would do afterwards, yeah. It only matters if you're doing sort of quantitative measurements. If you're doing relative measurements, the mass is sort of independent. The signal level doubled when we did this. You don't have to take it into account. Yeah. Yes, no. Yep.
Can you just talk a little bit more about the test plasma that you use and why that's maybe a little bit different to what customers would use when you go on site? That makes sense.
Well, it's designed for testing instruments. So we just want it to be stable, reliable, the same every time we put it on. We don't want to be sputtering anything or coating anything because it has to be sent out clean to the customer. So we try and limit what gases we put in. That's why for that zone H stuff, it was just water and the argon. I don't want to go putting ammonia in or something like that. So, yeah. Okay.
Any more questions? Okay, well, thanks.
Grant, no worries. I'll let you do that. You're better at driving. Okay.
So now we have May. Change to the. Yeah, please. Yeah. Go in this.
I have mine.
Can you just place this microphone on your shirt? Is that okay? Yes. Okay, all yours.
Okay, hello everyone. I'm Amir Apostol Faghari. I'm doing my master thesis in Fraunhofer IWS. Matthias Radolf, Abhishek Batsal, and Jennifer Cannon helped me in this regard. And the title of this presentation is Plasma Diagnostic of Radiofrequency Excitation on Industrial Dual Frequency Capacitive Coupled Plasma Etching Tool using Quadrupole Mass Spectrometry. Here you can see the outline of this presentation. I start with motivation, experimental setup, I speak about the tool and the plasma diagnostic tool. I go to methods, IDF summation, measurements, error, and conclusion. Let's start with motivation. Okay, to aid the development of process for back-end of line and interlayer dielectric, and due to the increase in material limitation and technical difficulties due to device miniaturization, we face problems such as edge uniformity, critical dimension control, edge selectivity, edge profile expansion, charge accumulation, edge damage, and pattern distortion. Here you can see a photo and illustration showing the interlayer dielectric. Here is the copper line, and this is the dielectric, and here is the front end of line. Yeah, and this is a trade-off triangle showing that the ion flux, radical flux, ion energy, radical flux, and byproducts effect on profile, selectivity, and aspect ratio dependence edge. So it's good to be able to control the radical flux and ion energy. So here there are two ways that can help in this regard, dual frequency CCP and pulsed plasma. And because the lack of knowledge about the plasma condition, I did plasma diagnostic. I start with argon plasma because it's simple and it doesn't degrade the tool itself. And I did some higher frequency and lower frequency variations, and I did experiments on pulsed plasma mode. And the advantages is it's in situ methods, non-destructive, and real-time methods. And it gives us insight on ion per radical ratio and control over ion flux and ion energy.
So now the experimental setup. So here is the schematic of the dual frequency CCP chamber with plasma diagnostic systems. I use a TEL Vigus LK3 chamber. It has two radio frequency generator, one in lower frequency and the other is higher frequency at 12.88 megahertz and 14.68. So I call this one LF from now on and this one HF. The QMS from Hiden Analytical EQP500 is connected to the chamber wall in the wafer level, and other diagnostic tool, high resolution OES and Sears from Plasmatrix is also available. So here I speak about the Hiden EQP500 plasma diagnostic tool. Hiden EQP500 mass spectrometer with energy analyzer. It can go to mass from range of 0 to 500 AMU. Mass spectra of neutral and ions, energy spectra of ions, RGA mode for neutrals, and SIMS mode for ions. Yes. So I mostly work with IDFs in SIMS plus mode. IDF shows how energetic active ions in plasma are, a snapshot of ion bombardments, energy being transferred to surface. Ion flux generated inside plasma is product of the integral intensity under the plot. So this is the IDF, and the integral intensity under this plot is ion flux. The IDF is mainly influenced by the transit time an ion take to cross the sheet, and by collisions the ion experience in the sheet region. And IDF depends on the following parameters: RF power, RF frequency, and chamber pressure. So here you can see a mass scan and an energy scan using the QMS tool. Now we go to methods. Dual frequency CCP, it can generate continuous wave plasma and pulsed plasma. This is a chamber, LF power and HF power, different decay time constant for ions, radicals, and electrons is different when the plasma is off. So this helps us with etching profile. So in continuous wave, you see the etching profile is different because of the opening here, but in pulse mode, because of the control over the ion per radical ratio, you will see this etching profile. So this is a design of experiment for continuous wave plasma. I did pressure variation in these pressures, 30 millitorr to 100 millitorr. Power variation for HF power 0 to 300 and LF power from 0 to 300. And I did sputter rates for all these experiments. Here is a snapshot of argon plasma mass scan. We will focus on argon plus and argon plus. Argon plus gives us the ion energy, because if inter goes into any collision inside the its way to the orifice, it disappears. So if we see argon 2 plus, it shows us the ion energy. And here is the process power variation. So I start with HF0 and LF variation and other powers. Okay, here is the sputter rates for all continuous wave. Here you see the effect of LF power, HF power at pressure 30 millitorr. How is the sputter rate different at different pressure? So I start with pressure. Why at different pressure the sputter rates are different? This is the IDF for argon plus 300 HF 300 LF. You see when the pressure is increasing, the IDF integral intensity and peak energy decreases. So in LF case, when the pressure increasing, the integral intensity at higher ion energy decreases and the integral intensity at lower ion energy increases. And in HF case, the integral intensity decreases and the peak shifted to the lower energies. So as the pressure is increasing, the average energy and the integral intensity decreases. So pressure mainly influences the ion collisions in the sheet region. And that's why we see less sputter rates. But when I check the VPP from the tool, I noticed these two plots. So what is VPP? The amplitude of the radio frequency voltage applied to the plasma. So when we change the power, this is the amplitude. And the difference in voltage between the maximum positive and maximum negative peaks within one cycle of the waveform. So when we change the pressure for RF power at higher frequency, we don't see any change in upper VPP. But when we change the pressure for lower RF power, we saw differences in VPP. So it is a tool, it adjusts itself when we change the pressure. So to see the real pressure effect, we run an experiment with constant VPP. So this is the before, constant power, 300, and here is constant VPP. So here you see the real pressure effect, just decreasing in integral intensity, and the energies are constant. Now I speak about the power effect, the LF power effect and HF power effect. Here is the effect of LF power only, so the HF power is off here. When we go from LF power from 100 watt to 300 watt, we see an increase in ion energies. So the ion energies increase in higher range. And also the argon 2 plus shows the increase in ion energies. This is the HF only. So the LF power is off and we only increase the power for HF frequency, and you see the increase in integral intensity and also increase in ion energies. And this is the effect of both LF power and HF power. So you see an increase in this direction. That's why we see two peaks in our IDFs. So the lower energy peak corresponds to the influence of the minimum sheet voltage, whereas the higher energy peak is caused by the maximum sheet voltage. And why we see these differences in the width of the peaks. At lower frequency, the ion transit time is almost equal to RF cycle, so we see more separated peak. And at higher frequency, the ion transit time is much higher than RF cycle, so the peaks are more unified. And ion respond to average sheet potential. And this is the influence of power on VPP. So when we change the HF power and LF power, the upper VPP just influenced by HF power, and the lower VPP is influenced by both of the HF power and LF power. And this is the conclusion for continuous wave. You see the HF power and LF power influence on ion flux. So ion flux is mostly influenced by HF power, and you see the HF VPP, which is the product of HF power, and you see it only corresponds to higher frequency. And the lower frequency caused having higher ion energies. So when the LF power is increasing, the ion energy is increasing, and you see this effect better in LF VPP. And here is the ion flux, ion energy, and sputter rate. So you see the sputter rate is depend on ion energy and ion flux, both of them together. And by combining the IDFs with sputter rates, we see the sputter threshold. This is my experiments, and these are the literatures. So for the case of both LF power and HF power on, we get 25 eV as a sputter threshold, and it's almost close to the literatures. And in the case of LF only and HF only, this is the sputter threshold. So far, I speak about continuous wave plasma. Now I'm going to talk about the pulsed plasma. So the tool can generate a pulsing mode for LF power and or HF power, or pulsing both the RF at synchronized way and with different frequency and duty cycle. So in pulsing mode, I speak about pulsing mode versus pressure, frequency, duty cycle, ion energy and ion flux comparisons, and sputter rate comparisons. The RF power for continuous wave kept at 300 HF and LF, 300 watt. I did pressure variation at frequency and duty cycle. So here is the influence of pressure on pulsing mode. In case of LF pulse, HF pulse, and sync pulse, for all of them, when we increase the pressure, the intensity at higher ion energy range decreases, and the intensity in the lower energy range increases. For all of the pulsing mode, this is the same. This is the influence of frequency on different pulsing modes. So in case of LF pulse, as the frequency increases from 0.1 kHz to 10 kHz, the integral intensity almost remains constant. In case of HF pulsing, the frequency increasing impact on lower integral intensity. And in case of sync pulsing, the frequency increasing impact on higher integral intensity. So the IDFs are here. And this is the influence of duty cycle on pulsing modes. As the duty cycle increases in LF pulse, the higher energy range integral intensity increases, and in the lower energy range, it decreases. But in case of HF pulsing, the integral intensity of the whole IDF increases, and in case of sync pulsing, the integral intensity increases and the lower energy range is not available. So here is different pulsing modes. Ion flux, ion energy, of different pulsing modes for different duty cycle. So as we increase the duty cycle to the continuous wave, we see HF pulsing as decreases in ion energy, LF pulsing ion energy increases when we go to higher duty cycles, and the sync pulsing decreases. And this is for different pressures. And this is the effect of duty cycle on ion flux. So the LF pulse has decrease in ion flux, HF pulse increase, and sync pulse also increase. This is the effect of frequency on ion energy and ion flux for HF pulse and LF pulse. As the frequency increases, the ion energy almost remain constant and ion flux almost remain constant. So the frequency doesn't have so much effect on the ion energy and ion flux in different pulsing modes for argon plasma. And this is the duty cycle effect on a sputter rate. So when the duty cycle increases, the sputter rate increases for different pressure, for HF pulse, LF pulse, and sync pulse. And this is the frequency effect on a sputter rate. So you see also the frequency doesn't have so much effect on a sputtering. This is the sputter threshold for different pulsing modes. So you see the sputter threshold in pulsing modes is a mix of different duty cycle and pulsing modes with both power on. Thus, we see so much difference and so much spread here. And this is the comparisons with continuous wave. So in LF pulse, we see this energy for a sputter threshold, for HF pulse and sync pulse, and this is versus continuous wave. So now we go to IDF summation. This is the IDF for LF pulsing 300 HF, 300 LF at duty cycle 50 DC. And these two are the two continuous wave plasmas. One is HF only, and the other is both powers on. And this is the resulting IDF with duty cycle 50, which is almost the same IDF as LF pulsing. So the summation of two IDF, two continuous wave experiments can be simulated with single pulsed plasma run, keeping the desired IDF shape from both. And it helps on recipe selection. So in case of summing both IDF and pulsing modes, this is the shape of the power. And this is here I speak about measurement errors. So the starting time of the IDF measurement after 4 minutes, after 10 minutes, and 15 minutes gave me different IDFs. So I always start the measurement at same time. And this is the IDF versus QMS position. So QMS is located on the chamber wall, but it's not always connected to the chamber, and it's located on a Z shift. So whenever we want to use the QMS, we connect the QMS. So here you see when it's 2 millimeter more inside or 2 millimeter outside, this is the resulting IDF. And always the QMS position kept the same. And here is the chamber environment. So we always run a same recipe, and whenever we see any changes in the IDF, we do chamber cleaning and chamber environment cleaning. Yeah. And we reach the conclusion. So pressure has major influence in ion collisions in the sheet region for continuous wave, and continuous wave mainly in continuous wave, higher frequency governs ion flux and ion energy influenced by lower frequency. So this is the main conclusion for continuous wave mode. In the pulsed mode, pressure increase causes shift to intensity from higher to lower ion energy in pulsing mode, and frequency has only a slight influence on duty cycle, and duty cycle has the major influence in pulsing mode. And from the sputter rates, I came to this conclusion that the sputter rates highly dependent on pressure and LF power and weakly dependent on HF power. Also, these sputter rate is codependent on ion flux and ion energy. A sputter threshold slightly varies between each position, each pulsing mode. A sputter rate is highest when both RF powers on, and with increasing duty cycle, the sputter rate increases. And this increase is sharper at lower pressure. Thank you for your attention.
Okay, so we have time for some questions.
If you have any questions. Yes.
What is the reason for this change in ion energy distribution with time?
With time.
Yeah.
It can be because of the tool itself. So the plasma condition can change over time, or it can be because of the QMS itself. It can be a problem with the extraction of peak like as a capacitor, and it doesn't give the voltage that we set exactly in a time, so the IDF might varies over the time. That's why we kept the measurement start time the same.
Yeah. Thank you for the nice presentation.
Thank you.
It was very interesting. And one question I have: how do you measure the etching rate in your process?
So I run a test for 1 minute etching silicon oxide, thermal oxide, and after 1 minute I used ellipsometer to see the etch rates.
And the question adding to this is: do you also measure the silicon? You have some neutral silicon in the plasma, I assume, and you should measure it, or could measure it too, and have some direct measuring of the etching rate, maybe, or etching volume.
I didn't understand the question. Okay.
Have you measured silicon in the plasma? Maybe not silicon ions, but neutrals?
In mass scans, you mean? Yeah, we saw traces of silicons when we started the process for mass scan. There was some traces of silicon also after etching. Yes.
Did you try to relate it to the etch rate? Correlate the amount of silicon that you measured during etching to the etch rate?
No, I didn't do that. Is there any more questions?
Okay, well, thank you.
Thank you.
Next we have Frank Kalfus from here.
So then, hello also from my side. We are from Fraunhofer IWS. This is where we are right now. We are hosting this event, or together with Hiden. They came to us, I think it was last year already, and then we talked about, or we asked, are there some meetings to discuss with other applicants of the devices, how they measure, what new developments are, and measuring strategy. I think this is the most important if you start measuring with the EQP as we did, and so we have to discuss a lot. And so the lifetime support by email, phone calls, and so on is very important. Then first you have to get this running, and then the measuring is done within a few days, but get it running, then you need for years maybe. But if you have some help and know the people you can talk to, then this is of course a great thing. This is the one I have to click on. I also want to introduce you to Fraunhofer and the Fraunhofer Society. I think this is the name giver of our institution. We have some very many employees right now. I think there's above 30,000 in Europe or in Germany and Europe also, and we have some branches in the US and other countries of the world too. And the concept of Fraunhofer is important, not only here. It's some role model also for other countries. They visit us and want to do something like this also in their countries. And why is this? This is the combination of the research we do anyway, the invention of new things, and the very important point is, as Fraunhofer itself did, he was also had a factory and had to earn money with his ideas. So we want to combine all of it and do some applied research and directly for the industry or very near to industry needs. And so they can make money out of our ideas or the things we develop together if they ask us for do so. This is what we are doing. This is the number I came up with earlier, or the last slide. Many people. The staff is including students also and full-time employees. Maybe there are 22,000 or so. And many people that we don't are allowed to give doctoral degrees, of course, but we are connected this strong to universities all over Germany so that we always have professors working at the institute as a head of the institute or leading some technology units. And so we are strongly connected. And so this is something we do typically all the time. These are, I think, 76 institutes and research units right now. Maybe since the presentation was made, it's changed a little, but this is the range. And 3 billion euros financial volume. This is a lot, of course. And what you see on the right side, it's the basic funding we get anyway, the 30%. And the other things we have to do industrial contracts or do public funded projects for this money. So we have to write proposals, of course, develop new ideas, find partners to develop it, discuss with the industry, discuss also in this meetings as we do today, find new ideas. What do we have to develop next? What's the next big thing? And of course, we have to be ahead of new topics that we can involve ourselves in the development of this. So the Fraunhofer IWS is not a large institute within Fraunhofer, but we have some 320 people here, and these are only full-time employees and 450 with students and part-time, also assistants, name it like this. And we are doing, it's Fraunhofer IWS, it's named for material and beam technology. With beam, this mean laser. We don't develop lasers, but we do all kind of laser processing technologies all around what you have. A test for cutting, for joining, and for structuring surfaces. It's important for many applications. And of course, we also do, this is what I do, we do also coatings, also different kind of coatings. We have the generative technology we are using also to 3D printing of ultra large scale devices for some space applications. And also this is a whole range we are working in. And the material is one of our base component to understand what the material does, what it can, how it can improve. This is our topic here at the IWS. So what do we have next? Now we have the outline of my talk. I changed the name a little. It's now only industrial scale carbon coatings with laser arc technology. We don't have to look at the applications because we are a user seminar and we want to look at what can we do with plasma measurements, what are the problems we have to achieve that. And so I put this more in the focus and also to prepare you for our lab tour later than at 2 p.m. So you already know how it's working, so we can then focus on the measuring technique and the results we see there. Okay, also the laser arc technology is our base technology for doing carbon coatings. Then I tell you something about EQP measurement requirements in our case and the results to it, and of course a summary at the end. So if you hear carbon and carbon coatings, a name maybe you have heard a lot is DLC. It's some overall name describing all kinds of carbon coatings, and they can range in a really wide range from graphite to diamond, and describes nearly everything when it's a coating, because the C in it's clear then it's a coating, but it's very different what it can mean. In our case, we can't do diamonds. We still have in our coating technique, we are generating amorphous coatings. And so we are out of the right side with diamond and nanocrystalline diamond, but we can achieve the coatings here named AC and TAC. Now the picture is missing. And it's in the range SP3 content from 20 up to 80. This is one advantage of our technology. We can get these kind of hard coatings. This is especially about the technology and also in very high rates. And of course, we are hydrogen free or nearly hydrogen free. So we don't have it in the chamber. Maybe if there is some leakage or so, then we have some very small amounts in it, but no hydrogen in the coatings at all. And so at the end, we got very hard coatings. Maybe now it's back again, the AC and TAC. You see the different bonding types. The darker ones are the SP3 ones, and the bright ones are SP2, the graphite-like bondings. Carbon is a very great material in this case, also for doing coatings. But what we did in the last time, we add additional elements. We doped our carbon, and so we can change anything, but there's one L too much down there, can add additional functions and modify the electrochemical and mechanical properties of the films by adding small amount of other elements in it in a low percentage range. And of course, in this case, we have a plasma containing carbon and additional elements, and so it's more difficult to measure this. Instead of only measuring carbon, we have to also look at other elements. And the heavier they are, the difficult it gets to measure it. So now let me introduce you to the laser arc technology. It's called LAM, and the M stands for modulus. This was an additional idea, an initial idea to make it adaptable to any coating chamber or at nearly any coating chamber. This is what you see on the left. We have some graphite cathode material, and this is what we want to evaporate. And we are working with some pulsed laser. This is the first picture in the left. For the ignition, it's some short pulse laser, 100 nanoseconds, to generate some initial plasma. And then we start an arc discharge with some high current. For, in this case here, 1.6 kiloamps is some usual number we are using. And then we have some spot splitting, as also it's described in literature a lot. And it's more difficult on carbon because we don't have a fast movement of the cathode spots on the surface of the graphite. So we have to stop this process after some milliseconds or some microseconds in this case, wait a little, or there is some time in between, and then we reignite it at a different position. And if we scan very fast, we have some linear carbon source after all. What are the advantages of our technology? We don't need magnetic fields for control of the arc spot. Otherwise, if you use DC arc, you have some magnetic field generator or some magnets on the backside, maybe adjustable also to get a good utilization of your cathode. And in our case, we don't need this anymore. And as you see on the right side, we have some new and some end-of-life graphite cathode, and we can utilize nearly all of the material because we can scan and we do use all in areas of the cathode as the same. This high volume targets also leads us to longer coating processes and very thick coatings. We can do 20-30 micrometer thick hard coatings for several applications where it's needed. And of course, you can use thinner ones also. Then the targets you need is only then in this case 1 per week or so, depending on how much you use your coater and how thick the films are. Okay, the combination with other PVD equipment is possible without a problem, but mostly people come to us and ask for a designated batch coater, and then we work with partners together to make this working for them. And what we also have, which is important, as you know, always if you have arc coatings, then you have the problem with the droplets in case of metal films or nitrides, oxides, and so on. And in our case, we have there is no solid graphite. It's then, in this case, these are particles. And so we have particles in our films. And if we do filtering, if we have plasma anyway, we can use magnetic fields to bend the plasma, as you see on the right picture in the bottom. Then we can do plasma filtering and get smoother coatings. This is how it looks like, the two types of our coating machines and plasma modules. On the left side, you have some high deposition rate variant, up to 2 micrometers an hour. Mostly we are limited then by the temperature we put in the chamber. If you want to grow carbon, you need to stay at lower temperatures, below 100 degrees C, and the higher you get in temperature, the softer your films get. That means at 180 degrees C, you don't get any sp3 coatings anymore. And then you have to cool your sample holder or have to reduce the deposition rate. So we could be limited also by this. We have some droplets or particles, of course, in the films. This is what we expect. And so it's mostly necessary to do some post-treatment of the surfaces. If there are like piston rings, they are very easy to process and also easy to grind afterwards, so that it's some standard process. And of course, there are applications when you are not able to grind anything or adjust the surface after coating anymore. If you think about gears, then you need initial smooth coatings to make this working. And on the right side, we have some scheme of such a particle filter. And as you see, the plasma is generated at the graphite. Then the particles are flying straight in some structure, and only the pure plasma is going to the deposition chamber. And so we get smoother coatings. But also, of course, if you have a filter, then you always have some reduction in deposition rate. And so we have 50%, which is good, but we still have particles in there. And in this case, then up to 1 micrometers per hour for a full loaded chamber. This is our equipment we have, one of our machines, and then you can also see our problem. We have some basic plant put in this case, its schematic is not in the right scale, of course. Then we have on the left side one module with filtering, on the right side one module without filtering, and so we can combine our coatings. But what we can't do anymore in this case, as you see, we can't adjust or adapt our plasma monitor anymore because all the flanges are adapted with some plasma sources already, and so in this case we can't measure at all. This is one problem we had, and we had to overcome this, and how we did this I'll show you later. And of course, special doped coatings we can also put in through the filter, so we can evaporate, and see also differences by the filtering, because our filter is usually ion energy selective, and so there are also effects if we evaporate doped cathodes in the system. And on the other hand, we can do all, on the right side, all kind of coatings. And what we also did is MOS2 coatings, which are working very well, and we got a much better adhesion at the spotted films. They are available on the market, and maybe there are an option for applications, but it's a complicated process for this, and I don't know if someone in the industry wants to do this, except there is this advantage of these kind of films, that it's making the cost valuable. Okay, this is some presentation, some video of our process, of our principle. This was the alarm modulus attached to the cathode, to the chamber. Then you here now see the scanning laser and the arc spots on the cathode surface. This process is very fast. It's 300 hertz, no, 150 hertz each cathode, and so at all you got some. You get some linear carbon source. So now we can also go to the street. And here you see now the plasma, and of course PVD or laser arc as PVD technique, it's line of sight. That means we always have to rotate our samples to make it coated all around. Okay, the EQP measurement requirements, as I told you before, we have to look straight in our plasma source. And we did some changes anyway. We developed some new filter with some 90-degree C deflection, and so we had a chance. In this case here you see this is the standard laser arc module, as I showed you before. And now we want to bend our plasma to the main chamber, which is shown here. But now we have all the options to look inside the plasma straight from the other side. We adjusted flanges to the side in the beginning because we know we want to measure it. But we can also do measuring from this side. There are also flanges attached in this, so we can measure the plasma straight and also the bended plasma by 90 degrees. But we haven't done this measuring already. We only adapted the device in here, and so we can do all the developments need for that. And here this is the scale, how it looks like, and our thinking is bend the plasma and avoid particles being reflected and coming back to or coming inside the main chamber. We are very flexible by our arc discharge, and we heard about some low power sputtering processes before, and of course we have some much higher powers. We have some 1600 amps, for example, at 80 volts or so. That means we got a lot of power in the system. And so also if we do the measurements later with the EQP, we have to reduce the frequency, otherwise we heat it up, and so we can't measure only for a short time. This is something we have to think about always. It's many different aspects we have to think about if you want to get some decent measurements out of it. Different kind of pulse forms we can adjust. Also to think about, we want to adjust the plasma exactly as we want. And of course, then we expect differences between some short pulse with some high current, as you see here. This is our more or less our standard. It's now rectangle named, but it's scene shaped also a little. And the other one is the thinking about this was reduce the current by the half and then make it twice as long. But in our case, I only show the results of this, what we have as plasma properties out of this pulse form. We have, as I showed you, short pulses here, the 300 microseconds also, but long breaks in between. And if you want to tune the device, you have to gate the measurements always, otherwise you don't get a signal. The system can't work with some time where no ions coming in, then it's for some reason, maybe it's the old software, maybe it's a principle, it's not possible to tune. You always have to gate. This is something we put in, and we use some gating with some delay and then some measuring window. And we also look what do we expect in what window. This is also some very important thing for us. But after all, it's essential for us to gate the measurements. This is one measurement of the current itself. Inside the chamber, this is the exact arc current I showed you before on the slide. It's starting with time 0, and then we have some sample holder here in the chamber after bending of the plasma, of course, 90 degree, and then we have some ion current. You see the different scale over here, and so we have some time of flight effect, of course, some at least 50 microseconds the plasma needs from the starting point to the substrate. And of course, the substrate is always put in with 100 volts bias voltage to avoid electrons coming in. And here, this is some effect you always see. First are the electrons, and then you have some small peak also. But the shape is nearly the same, and so this is what we expect. So now let's come to the EQP results. To remember, this is our plasma source here, our base chamber, and this is the place we are starting the measuring. And we did some no plasma redirection measurements in the beginning. And this is the graph of it. Here in the energy in electron volts. This is always easy possible if it's some single charged ions. Then you have to not think about voltage or electron volts. The count rates are good, of course, and I added this at 100% or put this to 100%, and then we did the plasma redirection active, and so we have some reduction of the surface under the plasma flux then itself, and then we have some 35% rest of plasma flux to the EQP. And we also measured, this was a total different process at a different time, the deposition rate at one sample here and one sample here, more or less same distance. And we see some, I name it similar, maybe it's 55 and 65.3. It's not this accurate, of course, we don't expect this, but we have the same range. We have 0.9 micrometer film thickness in the sample here and 1.4 in the sample here. That means we got a plasma transmission over 50% with our 90-degree filter, which is better than the 60-degree one I showed you before. And I think there are additional options to increase this in the future also. The next thing I want to show you, I started this in the beginning, is the multi-material evaporation. And so we put in different materials. In this case, we used some metals and non-metals in forms of boron and molybdenum. They are two examples. Boron as a non-metal, very light element, and molybdenum as a very heavy metal for different kind of applications. We had some thinking about in the beginning, why use boron? Boron doesn't affect the sp3, sp2 ratio this much because it wants to form sp3 bondings anyway. So it stabilizes, and in molybdenum, the thinking behind this was to make it or to adapt it to applications where you need lubricants with some molybdenum in it, and it forms some dry sliding components, molybdenum disulfide on the surface. And this was one of the thinking why we used the molybdenum. And the differences between, you can see here in the cross sections in the beginning, we have TAC with really rough coatings, and we have defect structures in the TAC coatings. In this case, they are thick, 5 micrometers. And if you do some break, then you see this structure. And if you go to TACB, we have the same hardness, means same sp3 ratio. And here we have some very smooth film without any defects anymore. And if you look to the molybdenum one, then you see also a smooth surface, and you see nothing as defects in it anymore. And two differences at the selected area diffraction you see up here in these pictures, you stay amorphous, as a carbon TAC is amorphous always, the TACB stays amorphous, and at AC molybdenum, it's some graphitic nanostructure we see in there. And this also, we can also use this kind of structure for several applications, but I come to this later. But here we have at all some effect of the heavy molybdenum, and some results of this I show you at the next slides now. First, we did some initial measurements of our graphite electrode, cathode, which we evaporated with the process, the pulse form I showed you before, the 1600 amps and rectangle pulse. And here we have now the ion energy in electron volts. This is correct. And for the C plus and C2 plus, and of course we know we have many parts of it in C plus and only a little C2 plus. And there are also effects, also thermal effects of our graphite cathode. That means if the cathode is very cold in the beginning, we got some larger amount of C2 plus, but if it's getting hotter and hotter, then it's get less and less. And so we always did some initial running in of the cathode so that they gain temperature, and measured after this always. And the average ion energies, this is some value we know from the literature also, and it's around the 30 eV for the single charged ions. Now this scale is now changed to voltage, and if you want to go to the electron volts, you have to multiply this with the ion state. This is 2 times ionized, so it's moving to the right side, of course. And for boron, it's the same. And if we compare this now to each other, the boron and the carbon, we see it's very similar, and it's also in the range for the 2 times charges and the single charged ions. And so this is something we see also if we use a plasma filter. We have the same concentration or the same relation between carbon and boron in the film, independent, or also if we do filtering or no filtering, it's always the same, because they are in a similar energy range, and so they are filtered the same. Now, if we go to the molybdenum one, it's only 5 atomic percent in it, which is not much, but it has a huge effect. And here we see some movement to the right side and some very large area or ion flux in the carbon plus. Here it's voltage. That means you have to scale this, of course, multiply by 2. And if we go to the left side, then we, of course, you have to do some measurement at each charge state of each element. Then you have to do the scan or set up one scan where you do all this at a time. And here, if you have the voltage, you have to multiply this by the charge time. The blue one stays the same, and the other ones are going far and far to the higher ion energies. And if we are now at the 4 plus, we are maybe at 200 electron volts, which is some very high energy of the molybdenum. And of course, it's also heavy, and this has some large effect on our carbon coatings, of course. What we see, also what we expect from the literature, we have some 2 times charge, 3 times charge. This is the dominant species as we expected also from other scientists. Okay, now I put it together also always the C plus for the 3 different cathodes. All the other process is the same. And we see now the reference in carbon. And then we see some movement to higher ion energies or some higher ion energies if we put boron in it. And if you put molybdenum in it, then it moves straight to the right side. And of course, we affect our properties of our films with it. How we do this, I haven't brought you here. I think this would be too much, but we can use this device very well for our measurements. And of course, if we go then to time resolution, then there are other questions we have, and it's still difficult to measure, but we are doing it, or I like to do it very much. And this brings me to the summary. Laser arc et al. Is a technique for industrial scale carbon coatings, and the machines are sold or running in industry at several sites. And the new customized TSE coatings allow new applications or many new applications. We have some interests in this already, and we want to understand or better understand the operation of these kind of materials and utilize this knowledge also in preparing the coatings for all kind of applications. So this brings me to the end. Thank you, and I'm happy to answer questions. I think I used the time very well, so we can do 7 minutes talking and then go for lunch.
Any questions?
Do you expect some problems when you have very high electron currents? Because we investigated similar systems with a retarding field analyzer. We had these problems with our high electron.
I don't know if this is a question or I can answer. I know.
Okay, yeah. So we can have a specialized version which can be up to 1,100 electron volts. So if we have a high current there, then that works okay. Where it biases the whole instrument up to the higher voltage, so it can deal with higher currents as well. So the energy filter is able to be driven externally as well as internally up to 1100 volts. So generally that's okay for higher energy plasma systems.
But the thing you
45 310, so any photons are high.
Is your question answered? I think I know what you mean. You have electrons also coming to the nozzle of the device, also electrons and ions, and then of course you heat up the whole system with the electrons, changing temperature and reducing accuracy of the device, and maybe doing some setup where you extract the electrons before, and you have some plate with some hole in it to reduce the electron rate to your system.
So the system can be supplied with an actively cooled shroud. So on the front end of the system, it can be actively cooled, so it can be kept at a constant temperature. Also, we can have some deflection there as well to deflect preferentially the electrons. So inside we have lenses at the front which can be set to repel electrons as they come to the front of the system as well. So the structure of the lenses is all tunable, so you can deflect the species before they even get further down into the system. And by the time they've gone through the extraction system and through the energy sector analyzer, then yeah, they can be all be repelled before they interact with any of the species, either internally or externally from the system. Yeah, there's a few options. A few options there.
And does the device have to operate it grounded, or can you also put it on some little negative potential? I think we only need some 10 watts or so.
Yeah, so it can be floated externally. The whole device can be floated. So normally it's grounded to the chamber, but it can be floated and isolated externally as well. So some users are floating to maybe 3 or 4 kilovolts to match their plasma conditions. So that's also possible.
Okay.
I was wondering about the bias current because
Yeah, it is low. It's only 1%, not 10% as we expect. It's low, yes. And we know we have to do some adjustments to increase the coding rate, also for the sample standing in front. That means also in this case the current is very low. It's, by the way, we operated with the 2-circuit system and using only the anode for the arc current, not the chamber anymore, and so we have this bad effect. And we thought also some years ago when we tested this setup once, it's really bad, and we have to adjust this where we have the electron sink in the chamber. This is the thing we want to look at next. But yes, it's too low. And of course, I can say something about the angle we are using, and we have some small sample, but it's still low.
I was curious, how do you bend the plasma at 90 degrees? How do you do that?
With some coil, magnetically.
Okay. Do you see some coating already on the coil?
The coil is covered, so there are no coatings on the coil.
Like electrostatic deflection?
The what?
Is it like some kind of electrostatic deflection of the plasma ions or species? How do you actually bend it at 90 degrees?
No, it's purely magnetical bended. Then you have some high flux in the middle of your coil, and this is bended by 90 degree. It's some Axenov principal filter type, which is well developed and used for at several coatings, nanofilms. They are building machines with some double 90-degree filters to achieve very smooth coatings, and we want to scale this for industrial applications for our linear source.
How do you deal with the addition of carbon on different surfaces?
On ours, sozusagen, in the chamber. No, we know carbon sticks very well to plastics, and we have some cold coating anyway, so we can coat plastics very well. But if you have metals, then you have to use some adhesion layer in between. Something which have some good connection to the steel, for example, which is chromium, and also carbon and chromium work very well together because they are forming nitrides, and so chromium is a very good interlayer for this. And we got very good adhesion and no problem at all in this case.
I also have a question regarding adhesion, but no adhesion in the measurement system. Since you have carbon measuring on carbon plasma, basically that also we have sometimes in our environment, and we have seen some issues with the position of carbon materials on inside the EQB system. So is this an issue also?
We don't have looked at the inside. We sent it back to the colleagues, and they sent it back to us and said there's no problem at all. Everything is still conductive. But yes, if you have high ionized carbon, then you have some non-conductive films generating, and you need only a few nanometers, and then you have no connection anymore. But this was not a problem. What we see, we have our orifice. We use a small one, at least I assume 50 micrometers. If it's small or not, this is something you know better. And we have to grind this all the time because we get thick coating on the nozzle and the orifice, also at short measuring times. We're only measuring for 2-3 hours or so between cleaning.
The experience that you have like a plasma exposure time for the orifice of like 2 to 3 hours.
Yeah,
And then
and you see that the signal is going down, and you have to do some initial measurement, then do your real measurements, and then you have to repeat the one you did in the beginning and see if it's still the same, if you have still the same transmission through the orifice to the device.
the grinding is done in-house here? Or
No, we do it by some adhesive tape, only clean up afterwards. This is working fine.
We're also using a mechanical shutter system, so it's just a shutter of metal sheet, and then we can just turn it into the plasma plum. So cover. So when we know, okay, we would like to make some initial evaporation process when we start, then it's not necessary to make a tuning process or something like that. So we use the shutter, and then after several minutes, let's say 30 minutes, we open the shutter back. And so we prevent the orifice to get covered by the PLC code. Thank you.
Yeah. Welcome.
Maybe from do you know the dopant ratio of your
Yes. No, we know it, of course, what we have in the cathodes initially, which is 5 atomic percent. And then in the coatings for boron, we have exactly the same, independent if it's filtered or non-filtered. And for molybdenum, we have some changing in ratio. Mostly we have some more molybdenum in the coating than it was originally in the cathode. But up to 10%, maybe 7 to 10, it's the highest. It does, yes. Of course, you have the heavy molybdenum. You expect some changes if you shoot the molybdenum deep inside the carbon. Then you have some sp2 rich traces or graphenic traces inside the material, which makes totally different properties. And we did EDX measurements of it. It's working good.
That low for EDX measurement. Usually for low atomic.
Then it's getting more difficult, of course. We also did, or not we, another Fraunhofer Institute in a project did XPS measurements of it, do some sputter deep scan and seeing what's the contribution or the distribution of the single elements within the coating depth. And so we see also we have not the highest amount of molybdenum on the surface. It's 20, 30 nanometers below the surface.
We did even a rather complex scattering, and so it's there without obvious.
Just to close this, have you seen solid solution formation?
It's not, it's this small. It's very difficult to measure, of course. With XRD, we don't see anything. That's what we expect, of course. No, we haven't looked in it this much to see exactly what we have, some nanocrystals of these materials. Maybe it's possible by fancy techniques, but we don't have it, and so we don't do it. And if we don't get it by selected area diffraction, then we don't want to look any deeper in it.
Okay, thank you. Thanks, Mike.
You're welcome.